Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aryabhatta College, University of Delhi. So in this lecture we are going to get hold of some more CPU scheduling algorithms, and in the previous lectures we have seen all the details about CPU scheduling, and we have also seen we have also listed the names of scheduling algorithms which we will be going through in detail, and we have seen first come first serve scheduling algorithm. So with upcoming the next one, which is the shortest job first or shortest job next, let me begin this lecture. So today's agenda is the CPU scheduling algorithm, and we will be taking the shortest job first, SJF, or in short this is also known as SJN, which is the shortest job next. Now the version, if we talk about, this could be in the preemptive form or this could be in the non-preemptive form, that we will be exploring in a short while. But as we have seen that in our first come first serve algorithm, there was a high waiting time. This is the we can say algorithm which is the best, which is having a good approach having a good approach to minimize the waiting time. So the advantage here of shortest job first is the waiting time is very less as compared to first come first serve, and it is also easy to implement in batch systems, but we need to know the CPU time in advance. So it is having an easy implementation in batch systems where the CPU time is already known in advance. But if we talk about an interactive system, and in these type of interactive systems the CPU time is not known in advance, so that means in these type of situation this is not we can say easy to implement, because we are not aware of the CPU burst. The requirement here is that the processor should know in advance that how much time the particular job is going to take. So if the length of the process, or we can say the CPU burst, is we can say known, that is perfectly fine, that is the input to the algorithm. And if it is not known, this algorithm cannot be implemented, because this algorithm associates with each process the length of the process's next CPU burst, or the length of the next CPU burst of the process. When the CPU is available, it is assigned to the process that has the smallest next CPU burst. So that's why this is known as shortest job first. So I'm repeating the key, the key line or the punch line, we can say. When the CPU is available, it is assigned to the process that has the smallest next CPU burst. So whatever CPU bursts are available, that we have already taken into account initially, whichever is having the smallest next CPU burst, that process is we can say assigned the CPU. Now what will happen in case of a tie? Let's say if we have the next CPU burst of two processes as same, then there will be first come first serve algorithm, which is the FCFS. We have already seen it in detail in the previous lecture. So that FCFS scheduling algorithm is going to be used to break the tie in case the next CPU burst of two processes is the same. So we can say another term or a more appropriate term for the scheduling method would be the shortest next CPU burst algorithm, because the scheduling depends on the length of the next CPU burst of a process rather than the total length. We are less concerned with the total length of the CPU burst of the process, but we are concerned with the length of the next CPU burst which is available. Now with this background, let us see an example. So we have set of processes with the length of the CPU burst given in milliseconds. So we have P1, P2, P3, P4 and P5 with the given burst time of 6, 8, 7 and 3. So here if you can see, we have the and here we are not considering arrival time, we are considering the uniform or the common arrival time for all. So the least CPU burst is of P4, which is of 3 second. Then we have P1, which is of 6 second, followed by P3 and P2 having 7 and 8 second. So we are going to schedule our processes like this only. So P4 will be given the control of CPU at the 0th time interval, that means as soon as the jobs arrive. Then after 3 second at 3rd time interval, P1 is going to get the control. It is looking for it is looking for CPU for some 6 seconds. So 3 plus 6 gives you 9. So P3 will be taking up after P1 and P3 needs it for 7 seconds. So 9 plus 7 is going to give us 16. So at the 16th time interval, P2 is going to get the control of CPU, and it will take up the CPU till 24th second, and then kind of releases the CPU because P2 needs it for 8 seconds. So P4 needs for 3, then P1 needs for 6, then P3 needs for 7, and P4 needs for 8. And waiting time, if we can see, 3 milliseconds for process P1, nothing for process P4, 16 milliseconds for P2, while 9 milliseconds for P3 in between, and 0 milliseconds for P4. So P1 is having some waiting time, so as P2 and P3, while P4 is not having any waiting time, because this was the shortest job shortest job among all which are submitted at a specific interval, at a specific point of time, we can say. So if we talk about the average waiting time, so average waiting time here is 7 milliseconds. So for example, if we were using the FCFS, which is the first come first serve, for this similar instance, if we would have used FCFS here in place of this shortest job first, the average waiting time would be 10.25 milliseconds, while the average waiting time in case of shortest job first is just we can say 7 milliseconds. So the first advantage of the shortest job first is that it is having a lesser average waiting time, at least when compared with the first come first serve algorithm. But the consequence here is we need to know the CPU burst in advance, but in FCFS this was not a kind of constraints, but FCFS is also first come first serve, is easy to implement. This is also kind of we can say it is easy to implement in the batch systems, this is not the algorithm for the interactive systems, we can say. Now why here the average waiting time has decreased? If we want to kind of see the reason behind it. So what has been done here? We have moved a short process before a long one, and that is going to decrease the waiting time of that particular short process more than it increases the waiting time of the long process, and ultimately the average waiting time decreases. I am repeating this once again, please understand. If we are going to move a short process before a long one, that is going to decrease the waiting time of the short process, and that is also going to increase the waiting time of the long process. But for example, let us say the short process is of 3 seconds and the long process is of, let us say, 30 seconds. So we have moved one process which was going to take place after 30 seconds, we have moved it to the initial state, and we have decreased its waiting time more than we increased the waiting time of the long process, because long process now in this situation also will be waiting for 3 seconds, while what benefit a short process has got is of 30 seconds. So this is going to give we can say a decrease in the average waiting time. Now coming to the nature of shortest job first algorithm, it could be preemptive or it could be non-preemptive. The choice arises when a new process arrives at the ready queue while a previous process is still getting executed. If the next CPU burst of the newly arrived process is shorter than what is left with the currently executing process. So, here is a trade off. If the next CPU burst of the newly arrived process, it could be shorter than what is left with the currently executing process. In this situation, if a preemptive shortest job algorithm will preempt the currently executing process, whereas a non-preemptive shortest job algorithm will allow the currently running process to finish its CPU burst first, even if the next CPU burst which has just arrived is smaller. So, the choice is between whether that process which is already getting executed is terminated or is we can say interrupted or not. So, if we see this preemptive shortest job first algorithm is the better term for this preemptive shortest job scheduling is shortest remaining first time scheduling, because on the basis of whatever time it is it needs the CPU more or whatever is the remaining time, that is important factor or that is the factor which is being compared with the CPU burst of the newly arrived process. So, preemptive shortest job first scheduling, preemptive SJF scheduling is also known as shortest remaining time first scheduling. Now, with the shortest job first, we have seen what is the strategy in what type of systems we are going to implement this shortest job first, what all could be the versions, what are the pros, what are the cons. It is we can say it is having a lesser average waiting time. Now, with this, let us explore one more scheduling algorithm, which is priority based scheduling. Now, priority scheduling is we can say is a non-preemptive algorithm, and it is one of the most common scheduling algorithm in the batch systems. Wherever the operating system is a type of batch system, the commonly scheduling algorithm is the priority scheduling. Now, we need to understand what is this priority. Each process will be assigned a number which is taken as its priority. Now, the process with the highest priority is to be executed first, and then the process with the next priority or the second highest priority will be executed next, and then so on and so forth. Now, let us say what if there is a kind of we can say tie, that means the process with the same priority arrives. So, the process with the same priority arrives will be this tie can be we can say this tie will be breaked on the basis of first come first serve scheduling. So, this is the tiebreaker which we have also used in our shortest job first. In shortest job first, if the two jobs were having the same CPU burst, we have taken the first come first serve as the tiebreaker. Similarly, for priority scheduling also first come first serve is the tiebreaker. Now, priority, if we want to define that that's a number, that's fine, but priority will be decided based on what? How are we going to say that this process P0 is having a priority of 10 while a process P1 is having a priority of 2, which is we can say it's a lower priority because higher the number, higher the priority. That's what the convention we are taking here. How are we going to decide the priority? So, there can be various ways of deciding the priority. Priority can be decided based on memory requirements. Priority can be decided based on the time requirements or any other resource requirement. So, if we have if we take a look at our shortest job first algorithm, that shortest job first algorithm is also a kind of we can say priority algorithm. Now, how it is a priority algorithm? Because the priority P here in case of shortest job first will be the inverse of the next CPU burst. So, higher the next CPU burst, lower is the priority. So, here is the reason which is given on the screen. If you can see here, it is shortest job first is simply a priority algorithm where the priority is the inverse of the next CPU burst. Higher the CPU burst, lower is the priority. Lower is the CPU burst, higher is the priority, and we can say larger CPU burst, lower the priority, and vice versa. Now let us say we have one more, let us take one more situation which is given on the screen with various process, burst time and the priority. So we have 5 processes named as P1, P2, P3, P4 and P5. We have the burst time there, that means the requirement of CPU in milliseconds as 10, 1, 2, 1 and 5 respectively. Also we have the priority. The priority of P1 is 3, priority of P2 is 1, priority of P3 is 4, priority of P4 is 5 and priority of P5 is 2. Now here we are taking a convention that lower the number, higher is the priority. That means we are taking priority as in sense of a rank, we can say. So here P2 with 1 as a priority will be given the first preference. Then we have P5 with 2 as its priority. Then we have P1 with priority 3 followed by P4 with 4 as its priority, and then P4 with 5 as its priority. So if you can see the giant chart here which is given at the bottom of the screen, we have started with the job P2 first, and then P2 with priority as 1 is looking for CPU only for 1 millisecond because its burst time is given at 1 millisecond. So starting from 0 to 1, it is going to take one CPU for one particular second. At 1 second, P2 is now has completed its execution, and now there will be the next job with the next highest priority, which is P5 with priority 2. So if we can see the burst time of P5, it is 5 seconds. So at the 6th millisecond or after 5 milliseconds, P5 is going to kind of, we can say, release the control of CPU. Then comes P1 with its priority 3 with a little larger burst time, which is from 6 to 16 of 10 seconds. Then comes P3 with 2 seconds of burst time starting from 16 to 18, and then comes P4 which is from 18 to 19 with the last priority, that is the priority 5, and kind of only burst time is only 1 second. So this will be the kind of execution schedule in this situation if we take the scheduling algorithm as the priority based scheduling, and we have taken 1 which is the lowest number as the highest priority and vice versa. Now priority scheduling can be either preemptive or non-preemptive, as we have seen in shortest job first, that depends on the next kind of coming CPU burst of the next upcoming job, whether the current job can be preempted or it cannot be preempted. Gives us the two versions of the shortest job first, preemptive shortest job first and non-preemptive shortest job first. Similarly, with the priority scheduling, it could be preemptive or it could be non-preemptive, but here is a major problem which says what? Major problem with the priority scheduling algorithm is indefinite blocking or starvation. So for example, let's say we have one job which is less in the priority, and there are kind of many jobs which are having higher priority, and these jobs are we can say these jobs are these jobs are coming on a continuous basis, and the one which is having the less priority is always kind of getting deprived of CPU because its priority is less. So a process that is ready to run and waiting for CPU can be considered blocked or can be considered kind of we can say waiting indefinitely, because the priority scheduling algorithm can leave some low priority processes low priority processes to and it is keeping them waiting indefinitely. So what is the solution of this particular problem? If there is kind of something which is kind of the higher priority jobs are coming on and there are the lower priority jobs in the queue and they are not getting their chance to take the control of CPU. So one idea here could be which is the we can say the solution to the problem of this starvation, which is a major problem if we consider priority scheduling algorithm as the scheduling algorithm for the CPU. The solution to the problem of starvation is that particular term or that particular solution is known as aging. So that this is the solution through which we can avoid the indefinite blockage of a low priority process, or we can avoid the indefinite blockage of or we can avoid the long starvation of a low priority process, and this process is known as aging. So what happens in this process, that this aging involves gradually increasing the priority of the process that wait in the system for a long time. So that's, let's say there is a process which is waiting in the system for a long time and the system is having some mechanism through which it is increasing the priority of the process automatically as the process is getting aged. So the process is getting aged, that means it has been a long time that the process is submitted, it is still waiting for its turn to come and it is getting aged. So the process priority of the process is getting gradually increased. So for example, if a priority ranges from let's say 139 which is kind of a low priority to let's say 0 which is a higher priority. So we have the processes which are having their priorities starting from 0 to 139, where 0 represents the high priority, 139 represents the lowest priority. So this 139 or the processes which are having lower priorities will never get their chance if higher priority jobs will keep on coming. So we could increase in the process of aging. What are we going to do? That we could increase the priority of a waiting process by 1 in every 15 minutes. So for example, let's say there is a process which is having the priority 139 and after kind of 15 minutes this priority will be equals to 138, then again after 15 minutes this priority will be equals to 137, then again after 15 minutes 136 and so on and so forth. So in this type of situations we can say with the calculation that after some kind of we can say 33 hours or something of that sort, this is going to this process which is having a lower priority of 139 will come to the higher priority range of 0, 1, 2 after some hours. The some hours here within this example of hours could be let's say 33 hours if we are kind of increasing the priority of the waiting process by 1 in every 15 minutes. But this is this kind of implementation of aging policy is a solution to the problem of indefinite blockage, or it is the solution to the problem of starvation in case of priority scheduling. So here in this lecture we have seen two CPU scheduling algorithms. One is the shortest job first, which we have seen, and it is based on the CPU burst, giving a relatively better average waiting time or relatively less average time. And then we have seen the priority job scheduling, which is suffering from the problem of starvation, and we have also seen the mechanism in order to kind of get rid of this starvation problem, which is the process of aging. So with this I would like to conclude here. Here is a list of references which is being used for the preparation of the lecture, and I will see you in the next lecture. Till then, take care, goodbye.